Lesson IN6, we're looking at linear equations. And what we're looking at, we've done before an equation y equals kx. K was our constant of proportionality, which was like our rate of change. We're just changing, instead of a k, we're going to do a m. So y equals mx. In this equation, y equals mx, m stands for the slope. I think it has to do with, in another country, their word for slope starts with an M maybe. I don't know that I ever found the full true answer to that, but anyway, that's basically what's happening. So if we have a proportional equation, then it's going to look basically the same. It's just that we're going to be saying that's our slope next to the x instead of our unit rate, instead of our constant of proportionality. They're all three really the same as each other, though, in this case. So if you look at this on IN31, a group of college students developed a solar-powered car and entered it in a race. Car travels a constant speed of 100 meters per 4 seconds. So part A, it asks what representation can show the distance a car will travel over time. So representation, basically, what's a way we can represent it in a way that we're going to be able to see how far the car is traveling over time. So in order for us to visually see how far the car is going over time, using a graph or table is probably going to be a good way of doing that. Graph is probably going to be the number one answer there, as far as visually being able to see that. So if we look at number 2, or part B, it says what expression can show the distance the car will travel over time. So an expression we've talked about before, there's going to be something, it does not have an equal sign in it if we write an expression. So the distance that the car will travel over time, we'll need to get our unit rate. So we talked about it's 100 meters per 4 seconds. So if we divide that out, that would be 25, and that means 25 meters per second. That's not our expression, but that's our first step towards getting our expression. What we could do now is think about, if they tell us an amount of time, how do we figure out how far it's gone? So for example, if it's gone for 2 seconds, how far did it go? So after 2 seconds, it would have gone 50 meters. We would do 25 times 2. After 10 seconds, we could do 25 times 10, would be 250. In general, then we could say 25 times x. So 25x is going to be an expression. And we would need to define our variable. So defining our variable, we could say let x represent the number of seconds. Then we know what that's standing for. The nice thing about having an expression is if somebody kept asking you, how far did it go in 3 seconds? How far did it go in 8 seconds? How far did it go in 15 seconds? How far did it go in 20 seconds? Okay, we start to get tired of that. And so besides that fact, it just makes it easier that we have something we can just substitute in place of our variable and figure out how far it's gone. Part C, it says compare the representation and the expression which shows the distance traveled over time more clearly. As far as showing the distance, probably the graph would do a better job of that. And again, we'd want to give a complete sentence here. We could say the graph because it's easy to see at a glance how far the car traveled at any time. So example 1, the students in Meg's class are building a fence around the class garden. How can they use the pricing for the different lengths of fencing to determine the cost for 50 feet of fencing? So they've given us three amounts here. One of those is not 50 feet, so we can't just look at the picture and say, oh, 50 feet, it's this much. We actually have to figure something out here. So what we could do, one option, the book doesn't do it this way, we could just look at what our unit price is. So $30 for 6 feet, we could divide that out, which would be 5, so that means $5 per foot. What we need to really do here, just to be sure, is to check these other ones while we're at it and make sure that they all come out the same. Sometimes with places you can get bulk discounts, like if you've ever been to a hardware store like Lowe's, Home Depot, Menards. Sometimes you'll see on the shelf there'll be, you know, this price, and then it'll have a contractor price or something. Check it out next time you're there if you have never seen that. So maybe it's normally 25 cents, but if you buy at least 10 of them or something, then it's 22 cents, something like that. Which, you know, for small stuff might say, well, it's not that big of a difference, but, you know, if you're buying stuff a lot, that's going to eventually save you a lot of money potentially. Okay, so anyway, we can divide this out with all three of these. All three of them happen to come out the same, so there's no discount being given here. It's $5 a foot regardless how much we're buying. So if we come over here, finding for 50 feet, it's 50 feet times $5 a foot, which would be 250 feet. One way just to double check yourself to make sure you're doing this correctly, we'll get into this, you guys will get into this especially more in high school, but we could say 50 feet and it was $5 per foot, and that 50 feet we can put over 1. You can actually cancel units out, just like when we multiply and you can reduce numbers down. It's kind of the same idea, and you can see what's left over is just dollars. So when you work it out, you can see just dollars left, so that's a good indication that multiplication is the right step, the right choice to work that problem out. So if we look what the book did, they just did this kind of a different way. Again, not really a big fan of these triangles underneath here, but a couple of these they gave us information. For 15 feet it was $75. For 6 feet it was, for 6 feet it was $30. 24 feet is $120. So what we could do is take two of these points. So if you just do the 630 and the 1575, we could look at what's our change in Y, what's our change in X, and you can see that's $45 more for 9 more feet. So, and then 45 divided by 9 is 5. But again, like we talked about earlier in the chapter, you know, if you graph this line, you can see it goes through 0, 0, and it's a straight line. Then you know it's proportional, and then you could actually just take the Y divided by the X, and that would tell you your unit rate. One other thing we could do actually in this case, if you have your line perfectly drawn, you might be able to look, if you graphed this far enough out, you might be able to look and see that this hits the point 50, 250, so 50 feet is 250. Okay, that's another option of doing this. The book basically then took that $5 per foot, like we found a little bit differently than them, and then they just used this. Like I said, we're talking about Y equals mx is what we're looking at in this lesson. In place of m, we're going to substitute our slope, which was 5. So Y equals 5x would be the equation for the line. And then for 50 feet, we can substitute that in place of the x and figure out that it would cost $250. All right, so several different options, several different ways that we can work this out to get that answer. So on the try it, they want us to write an equation to describe the relationship shown in the graph. In order to write the equation, we're going to have to find our slope. In order to find the slope, we're going to have to find 2 points on the line. So any 2 points on the line are fine as long as they hit directly on the line. This one happens to have lots of choices. So 2 points that this line goes through, 120, 240. Yes, we could use 0, 0 as well here. There's other points up the line also that would work. Just to make things interesting, maybe let's use the 120 and the 240 just because we're not always going to be given 1 through 0, 0. Just to get some practice with that maybe. So slope, it's the change in y over change in x is what we need to find here. So change in y, if we look, our y value went from 20 to 40. So our change in y would be 20. And again, working that out, you could say 40 minus 20. Change in x, the x went from 1 to 2. So for that, we could do 2 minus 1, which is 1, as our change in x. So we went up 20 over 1, so our slope is 20 over 1, which is the same as 20. Really, the hard work has been done at this point. That's our slope, which we can actually call m. And then our equation that we're working with, y equals mx. So our equation would be y equals 20x. So really, like I said, large majority of the work really is done just by finding the points, finding the slope, and then it's kind of just the finishing touch of actually writing your equation there. Since this line goes through 0, 0, it's a straight line, we know it's proportional. We've talked about a unit rate point, which is right here at 120, which tells us that we know it's going 20 miles per gallon. Okay, 1 gallon, it went 20 miles. So you could actually technically use that point as well. Okay, again, just to get some practice, probably not a bad idea. You know, if everyone's like that and we're always using that point, might not be a bad idea for some of them at least to actually work it out by hand and make sure you understand how to do it that way as well. So back here, if you would have filled in the boxes, that would have been using certain points, and that would have been 80 minus 60 over 4 minus 3. That'd be using the point 480 and 360, and that also would be 20 over 1, which is the same as 20. So again, as long as you pick 2 points that are definitely on the line, then you're in good shape. So again, y equals 20x was our equation. Example 2, a line has a slope of -1/2. The point 4, -2 is on the line. Use the point and the slope to graph the line. So in order to do this, like the book says, the first thing we would want to do is actually graph that point 4, -2. So remember, 4 is the x, -2 is the y when you go to graph that. So once we've graphed that point 4, -2, the slope is -1/2. So what we're going to do, we're actually going to go from that point, we're going to use the slope to find another point on the line. So slope's change in y over change in x. We've talked about before, I don't care for the negative sign being right next to the fraction because it can blend with your numerator, or blend with your fraction bar. I'm going to put it in the numerator. So let's say that's -1/2. So if my slope is -1/2, my change in y is -1. So from that point we go down 1, that's -1. Change in x is 2, so we go over 2. That gets me to another point. And once I have 2 points, I can tell what the line's doing. So this is technically what the line is. One thing the book doesn't do that I might add is an arrow going the other direction. There's nothing to make me believe that we can't continue up into the other quadrants as well. Some real life cases you might be restricted on some parts of the graph not making sense, but in this case I think we're okay there. One thing about this, looking at our slope, we said the slope was -1/2. Looking at that graph, it does look like a negative slope. One thing I may have forgotten to mention to you guys is looking at the directions of the slope. A negative slope is this first one, and a negative slope, we could make that into an N for negative. And then positive slope, we could kind of make that into a P for positive. The better one is making the N for negative, because we could kind of make either of them into a P, you could argue. But N for negative, the other one's going to be backwards N, doesn't work.